We'll go ahead and get started here. Hello and welcome everyone to our webinar. My name is Andrew Mills and I'm a research scientist at the Lawrence Berkeley National Lab, and I'm going to be introducing our discussants today. And thanks for joining us. This is a webinar on a recent paper that was published in the Electricity Journal on the motivations for hybrid systems in the US. There's a link that's shown here on the slide in front of you where you can download a copy of this paper for free. It is open access. I've also provided a link in the chat to that and also to the slides that we're going to be presenting today. This paper was authored by researchers from the Lawrence Berkeley National Lab and also the Electric Power Research Institute, or EPRI. This is part of an ongoing project. This is the first phase of it. And so we do welcome your feedback, and please also be on the lookout for additional papers are going to be coming out on this topic. So for the logistics for today's webinar, all of the people will be in listen-only mode. So what we're asking is that if you would please use the Q&A functions that are on should be the bottom of your screen to ask any questions that you might have. We'll save about 10 minutes or so at the end of this to go through those questions. In the meantime, if you have any technical issues or anything like that, please try us on the chat. We'll be monitoring that and trying to help you out with that. The speakers for today are Will Gorman and Eric Ila. Will led the paper and is a graduate student researcher with the Lawrence Berkeley National Lab, where he's been with us for over a year now. And he's also a PhD student in the Energy and Resources group at UC Berkeley. Previously, he worked at the Brattle Group and has a Bachelor of Science in Chemical Engineering from the University of Texas at Austin and a Master's in Energy and Resources from UC Berkeley. The other presenter is Eric Ila, who's a principal manager at the Electric Power Research Institute, where he currently, one of the projects he has that's related to this is that he's facilitating an R&D collaborative group of technical experts of North America's ISOs and RTOs. Previously, Eric worked at NREL and also the New York ISO, has a PhD in electrical engineering. With that, I'm going to turn it over now to Will Gorman to start off our presentation.
Great. Thanks, Andrew. Thanks for the introduction, and thanks everyone again for joining. We hope that this webinar will be informative for you all. So just to provide a little bit of a roadmap of where we're going to take you during this presentation, I'm going to quickly introduce the topic and motivate the reason that we pursued this research and kicked off this multi-year effort to understand hybrid projects. Then I'll jump into a qualitative discussion of the pros and cons of hybridization, in particular focusing on the pros and cons as compared to independently siting storage and generator projects in different locations. Then we'll discuss some of the quantitative trends that are happening regarding development of these hybrid projects in the United States. And then the last section that I will present on is the section 4, where we discuss PPA prices that we've been seeing in the market for these co-located generator plus battery projects, as well as a simple optimization model that we've built to understand potential dispatch strategies for these projects in California and in Texas as a means to compare the market value of these hybrid projects to the PPA prices that we've been seeing. At this point, I'll kick it over to Eric to present the work that him and Nikita Singhal worked on wholesale market participation issues for these hybrid projects. So the reason for studying this issue is, on the one hand, the big industry trend in the electricity sector over the last 10 years have been growing levels of variable renewable energy, and a growing understanding that as we increase the penetration of these technologies, we will need strategies that enhance grid system flexibility. And storage has come out as one of the big technologies that can be used for this enhanced flexibility, and due to the declining costs of batteries in the last 5 years or so and projections of future cost declines, they've become a very popular choice for providing this system flexibility. At the same time, there's been a big commercial trend that has kind of taken off in the last few years, really recently, where developers have increased their interest in co-locating generation with batteries at the point of interconnection. rather than siting separately. And so because of this huge commercial interest, we have found that kind of studying this issue has become very important for the industry. And in addition to these kind of high-level motivating themes, there's also a lot of work happening right now in both the ISOs and at FERC to understand hybridization, as well as implement new rules to integrate these technologies effectively and efficiently. And so because of this, we've been hearing that there has been a big need for information on both the advantages and disadvantages of hybridization, their development trends, their cost and value, as well as some options for their ability to participate in wholesale markets, and the challenges that come with those variety of options. And so the proceedings that we've been reviewing and thinking about here are FERC Order 841, which is a huge proceeding order that FERC had a few years ago. But in this order, they didn't explicitly talk about hybridization. They focused mainly on standalone storage. And there have been calls, for instance, from Commissioner Glick at the FERC for grid operators better understanding and coming up with market contracts related to hybridization. At the same time, the ISOs have kicked off relatively recently working groups and have written proposals for how to integrate these technologies. And so California, kind of one of the leaders in this space, kicked off their work late last year, but all of the other ISOs are starting to do the same. So New York and MISO. And so it's important that as these kind of rules are getting formalized, that there's some grid research to help inform that work. And before kind of jumping into the bulk of our results, it's important to kind of scope down what we focused on in this research. And so we will only be talking about battery plus generator hybrids, mainly due to the commercial interest in these particular applications. So when thinking of hybrid projects more broadly, people oftentimes discuss concentrating solar power, which has a form of thermal energy storage and solar technology. You can also think about combining wind and solar or PV in a thermal generator. And so there's a lot of different ways that you can define this term, hybridization. For this research in this paper, it was not the focus. We weren't trying to come up with the end-all definition. We really just wanted to focus on a particular class of hybrid projects, which is co-located batteries and generators. But as Andrew mentioned, this research is part of a multi-year effort, and there will be additional papers that come out to help further explore the whole kind of space in hybridization, but this paper will just be focused on battery plus generator hybrids. So now let's move on to discuss some of these pros and cons of hybridization that we created. And the list that we came up with is on the left in this graphic that you see. But before walking through these different pros and cons, I want to give you just a sense of how we came up with this list. And we were mainly focused on economic arguments for hybridization as compared to standalone plants. And that kind of informed how we were thinking about this, because we really wanted to think about how potentially developers would be able to take advantage of different economic incentives, as well as how the system kind of level impacts would be made on this economic side. And so this last point is important because all of these drivers of developer interest does not necessarily mean that the economic advantages to developing the projects reflect true system level economic advantages. And so one kind of quick, easy example to state this point is the federal investment tax credit, which is an upfront tax incentive to install and co-locate hybrid projects. But this is just an incentive that goes straight to the developer and is not necessarily aligned with some true system level economic advantage. It's just an advantage it has for developers over standalone power plants, standalone storage and generator power plants. So that's something to keep in mind as we go through this list. And so for the pros of hybridization, we broke it up into two categories, the first one being cost synergies and the second one being market value synergies. And on the cost side, that first bullet kind of references the investment tax credit for the most part, that some hybrid projects currently qualify for more financial incentives. And so this happens if the solar plant or wind plant, if you decide to take the ITC, if it charges at least 75% of the energy, if that energy comes from the solar or wind plant into the battery, you qualify for the ITC. And so that's a big kind of cost synergy. The other cost synergies are with shared permitting, siting, equipment, interconnection, transmission, and transaction costs. And so when you're developing these projects and building these projects, there are kind of overhead and construction costs that are fixed in some ways. And so by hybridizing, you have the ability to save on those costs. On the market value synergies side of things, we found, as we were reviewing the different material out there, that there could be policy-driven market design rules which could end up valuing hybrids more than standalone batteries. And so these rules are currently getting developed, and so there's no one rule that we really want to point to right now that is illustrative of this issue. But you could imagine that as these rules are getting developed and constraints are being put on either standalone storage or a standalone wind or solar farm, for instance, on what kind of market products they can provide because they're energy limited resources like storage, or capacity limited resources because of the variable nature of wind and solar, but there could be some constraints on what markets that these can play in. But when you hybridize these technologies, that additional capability may lead to market design rules that the hybrid projects can take advantage of. And that's really what we were thinking about at that point. The other 2 points that we have here are abilities for batteries to kind of improve the operation of generators. And so the first one is thinking about, in particular, types of clipped energy that might happen, especially when a PV plant is generating, in terms of the AC constraints on the inverter side of things. And so there are times when the PV plant might be producing and the inverter wouldn't be able to kind of export that energy to the grid, but a DC coupled battery might be able to take advantage of that energy and store it rather than waste it. And so this is also kind of thinking about curtailment and issues like that. For thermal generators, we've also heard and seen that batteries can reduce wear and tear from generator cycling, especially when you're thinking about ancillary services. Then to go into some of the cons of hybridization, we see two big operational and siting constraints when talking about this. And the first one is reduced operational flexibility. And so this is the idea that, somewhat related to the ITC, that when you decide to co-locate and you constrain the system to charge the battery only from your wind or solar plant, in particular to meet the ITC, that reduces some of the operational flexibility and the ability to arbitrage on the grid because you've implemented that constraint. Now that constraint might go away in the future if the ITC gets granted for storage, and it does go away after the first 5 years of the project. And so this isn't necessarily a constraint that will remain forever, but is one that exists today. The second constraint, which is an important one, and potentially the more important one, is that you are potentially in a situation where you suboptimally site your battery away from congested areas or away from the areas on the grid that have the most arbitrage value. And that's because, you know, the decision to site a thermal or a renewable generator is depending on fuel availability, and it depends on, you know, the capacity factor and the resource availability of wind or solar. And it doesn't necessarily depend on the optimal placement on the grid where there is congestion and where the battery could be most valuable. But the decision to co-locate and make that decision, siting decision in one kind of power plant is an additional constraint on these systems. So those were the pros and cons that we came up with when thinking about hybridization. But again, want to reiterate that there is a lot of regulatory uncertainty, especially on the market design rules and related to the financial incentives that will need to be thought about in order to know whether or not this trend towards hybridization kind of will continue, or what it will look like in the future. So let's go ahead and move on to what those development trends look like now, at least. And the first results that we want to present are the amount of gigawatts installed that are currently online and the ones that are being exist within the immediately development pipeline. And so that's the graph that you see here. On the left is the current installed capacity of hybrids. On the right is the pipeline capacity. I think one of the first things that jumps out of this chart is the enormous growth kind of in all resources except oil in the immediate pipeline, but especially in PV plants. So we have seen a huge move towards development of PV hybrids. Today, there are 61 online hybrid or co-located projects that are larger than a megawatt. And there's more wind and gas hybrids than there are PV. But in the near-term pipeline, there are 88 projects, with the majority of those being PV. And so some other things to think about here are comparing the different colors in this bars. And so what we show here in the lighter blue color is the battery component of the hybrid, and then the darker color is the generation component. And so there have been characteristic trends that differ kind of across time. And so what we've been seeing is that the battery to generation ratios, as well as the battery durations, are larger for PV hybrids as compared to wind and natural gas. And they increase from installed to pipeline projects. So the durations and the battery generation ratios have been going up, which is likely explained due to the decreasing costs of batteries. And the other important characteristic to mention here is that the majority of the batteries that are being installed are based on lithium-ion technologies rather than lead or sodium-based technologies. And so this is kind of this is the online capacity. It's the immediate development pipeline. So you should think about projects that might be entering construction or operation in the next 2 to 3 years. These data were taken from EIA's Form 860 and analyzed to form hybrid projects. But there's another set of data, which I'll show on the next slide, which is the interconnection queue data. So the data on the prior slide was all EIA data, and all data that we could identify was either online or in immediate construction. And this queue data it's much more uncertain in whether or not these projects will get built, but there is also a lot more activity in these queues. But the first story that the thread that was brought up on the prior slide of PV hybrids dominating, that story is also the same one in the interconnection queues. So what you see here is data from the 7 ISO RTO interconnections. And on the left side, you see the total capacity that is in the queues. And the lighter color is just the standalone capacity that exists in these queues. And the darker color is the amount of hybrid capacity, or the amount of that standalone capacity that is getting paired with a battery. And so you can see that 25% of all solar PV in the interconnection queues is being paired with a battery. And that drops significantly to 4.3% and 1.3% for wind and natural gas, respectively. But in total, there is 70 gigawatts of hybrid generator capacity in these queues. And the blue chart on the right, this is looking at kind of some of the time trends of that generator capacity. And we found that the majority entered the queue in 2019. And so this is mainly to make the point that of this hybrid capacity, it is recently being proposed and recently being, the interest is just more in the near term. And we also compare it on this slide to the amount of standalone battery capacity, which is also quite significant. So now looking at this same data, the same interconnection queue data set, but the regional analysis, we found that CAISO is the leading market among ISOs in terms of PV and wind hybrids. So in CAISO for 2019, 96% of PV and 75% of wind are paired with batteries. And over all application years in CAISO, 67% of PV and 50% of wind are paired with batteries. So a huge amount of interest in California. And you can see that data that I just mentioned in this green table on the right. You can compare it to the other regions in the United States. And you can see that really CAISO is the only region that has interest in wind hybridization, though there are a few other regions where it exists. And there are more regions where there's a significant amount of PV hybrids. And there's many reasons that this might be happening in California. California has the largest penetration of solar PV as compared to any other region in the United States. And so this, the quote unquote duck curve that exists there affects market prices in a way that might benefit hybridization, or at least benefit batteries in general because of the arbitrage value. And what we'll see a little bit later in the next section is, in our simple optimization analysis, we kind of show how the California market has a much higher value premium for battery technologies, for hybrid technologies, than Texas. And so that, in a way, kind of informs this trend. So let's go ahead and jump into that price and market valuation. So first, the first two slides, I want to talk about PPA price trends. And so these are PPA prices that we were able to find for PV battery projects over the last 5 years. And so this chart on the right shows that the costs have been declining as the cost for these technologies, solar and batteries, have declined. In Hawaii, they dropped from $120 a megawatt hour to $70 a megawatt hour, and a similar halving of PPA prices in the southwestern portion of the United States. And you can see, we've broken up between Hawaii projects and other states to give a sense of how there is a premium in Hawaii, which could be driven for a variety of reasons, but might be attributable due to either higher construction costs, higher battery to generation ratios, or, since these are PPA prices, due to the higher cost of electricity in Hawaii, and the fact that the competing kind of technology, quote unquote, is the grid. And so the PPA prices are higher there. For 6 of these 23 projects that we just showed, we could take out a battery adder or a storage adder for those projects. So basically separate the cost, the PPA price that is affiliated with the PV technology, and the PPA price that is affiliated with the battery technology. And that's what you see here on the graph. And the x-axis is a function of the battery capacity, so the battery to generation ratio. And you can see a range from as low as $4 a megawatt hour to as high as $14 a megawatt hour, in a fairly linear trend. So as you add more batteries onto these projects, the storage adder gets higher. And keep these numbers in mind, because these are the prices and the costs that we're going to compare to our market value analysis that I'm going to show you shortly. And in particular, since we focus on in our optimization model, we focus on a 50% battery to PV capacity ratio, keep that $10 a megawatt hour delivered in these PPA price storage adder in mind. And so now let's jump into this optimization analysis. And so I know there's a lot on this slide. I'll walk you through it, but if there are particular questions, do feel free to ask them, and we'll try to get to them at the end of the presentation, because I won't be able to walk through all the details. But at a high level, what we did here is we took three general inputs, which are market prices, and we used market prices in Southern California and the West Hub in Texas, hourly prices, and we combined those with hourly variable renewable energy profiles, so wind and solar profiles in both of those two regions, to come up with our time series data. And then we combined that with some battery constraints to understand how these hybrid batteries would operate in wholesale markets. We combine all those together, and we run an optimization to calculate the hybrid project market value. So some of the system specifications we used a 4-hour AC coupled battery. It's sized to 50% of the renewable capacity. And we have, for this kind of first cut analysis, we assumed no battery degradation costs. The optimization model, I think it's important to realize that we had 2 algorithms to dispatch these technologies. The first is perfect foresight, so it's the best case scenario where we assumed the storage would dispatch itself to maximize real-time energy market revenue, and it would know the VRE profiles in advance, and it would know the market prices in advance. So that's the optimistic case. We also have a low case, or the pessimistic case, where we schedule our batteries based on yesterday's prices, which an operator would know, but we multiply the schedule by today's real-time prices. So this is based on yesterday, what would you do today? And that's the revenue that you get. So this is our low case that we do. And so there's a number of other battery constraints that we implement to make sure that everything's balanced. But at a high level, this is the optimization that we created. So now let's jump into the results. And so just to orient you on this slide, on the left side, there is PV results. On the right side, that's wind results. And then internal to all of these, we break it up by region, so California and Texas. And then within any region, we show the difference between the generator standalone results and then the market value premium for adding a battery onto that result. And so you can see on the very left, you see California. When you add a battery, you get almost a $30 a megawatt hour market value premium for that project. And so remember, I said keep that $10 a megawatt hour number in mind from a few prior slides. That's the number you want to compare to this difference. So because we saw that $10 a megawatt hour was the PPA price increase, we found when you're using this perfect foresight dispatch algorithm that you could get a $30 market value premium. Now that's in California. I think one of the big results that we see here is that there is a big difference between the California market value premium and the Texas value premium. So this is getting a little bit back to what I was talking about when thinking about the duck curve and the high penetration of renewables that we've already started to see in California, and how that might be one explanation for this market value premium in California. And so those are some of the big kind of takeaways to see here, is the differences of cost markets, as well as the very small difference across technologies when you compare PV to wind. But the other point I want to show and make here is these gray ranges that we present here. So I said that we had multiple algorithms. So the top gray range is actually using the perfect foresight algorithm on 15-minute prices rather than hourly prices. And so there's a little bit of a value boost when you go down to 15 minutes. And then the bottom of this range is when we're using this day-ahead persistence schedule, where you use yesterday's prices to schedule in today. And so that does chop the value kind of in California from this $30 a megawatt hour all the way down to $13 to $16 a megawatt hour. So this dispatch algorithm is a kind of a critical piece here to understand the market value of these projects. The last slide that I want to talk about is a comparison of the standalone generator and storage technologies as compared to hybridization. So on the prior slide, we were looking at a standalone generator to the hybrid projects to see what the storage premium is for those projects. Here, we want to see what the kind of reduction in value that comes from adding additional constraints onto the hybrid project. So remember when we were discussing the pros and cons, we were talking about some of these additional constraints. That's what we wanted to see what the hit was to the value here. And so it's the same kind of structure on the figure, but you can see this reduction is driven by the market value for standalone PV and standalone storage stacked together, and then what you get in the market for a hybrid project. And there's two constraints that really drive this difference. And so to fix the ideas, really just want to focus in on why this reduction occurs. And the first reason is that in our battery constraints for the hybrid, we do not allow it to charge from the grid. And so when it can't charge from the grid, it doesn't have as much arbitrage opportunities. And so that is a reduction in value as compared to standalone, what a standalone storage unit would be able to do. Now, of course, this would disappear or be relaxed in a post-ITC world, depending on how you configure the hybrid. So that's something to keep in mind, that that constraint might not exist all the time. The second constraint that we implement here is a point of interconnection limit. So when we were reviewing the Q data that I was discussing earlier, we found that most of these hybrid projects, when they're applying to interconnect on the grid, are applying for a transmission size or POI limit close to the size of the generator rather than the sum total of the generator and the battery project. And so what that means is that the point of interconnection is smaller on these hybrid projects. than the separate projects, and so we've implemented that constraint here. Of course, that is a developer choice. They avoid paying for that additional transmission, so that's a cost saving, but there is this additional constraint that reduces value. Now, the one constraint that we think is very critical, and is one that we want to look at for future work, but one that we did not implement here, is that we did not do a comprehensive geospatial analysis to understand where the optimal location would be for standalone storage if it was able to be installed separately from a PV plant. So this analysis assumes that the hybrid and the separate technologies are installed at the same node using the same renewable energy profile. Now that likely understates the value of standalone systems, and so will understate the value reduction due to hybridization that you see here. So that's something to keep in mind, and it's something that we're looking at in future work as we expand this type of simple optimization analysis to many more nodes in the markets across the United States. And so with that, I think it's a good segue to move into Eric's portion of the presentation to talk about how these hybrid projects would be able to participate in wholesale markets and some of the participation issues that arise with that. So with that, Eric, I will turn it over to you.
Thanks, Will. Just to introduce this part of the research, so large part of this research related to hybrids was to evaluate the different potential participation models that may exist and what their structure may look like. So participation models, some of the folks here may have heard the term. It's a term that gained some attention following the FERC Order 841 on participation of energy storage in organized electricity markets that Will mentioned earlier. It refers to the set of tariff provisions, software bidding, and other features and rules that accommodate the participation of resources with particular physical and operational characteristics in the organized wholesale electricity markets. That order was, was laser focused on standalone electric storage resources, as Will mentioned. While it did say that hybrid resources can use the electric storage resource participation model, it did not explicitly account for any of the unique characteristics that hybrid resources have that are different from the standalone electric storage resources. And as Will mentioned, also, many of the ISOs in other regions are now initiating stakeholder discussions about participation, operations, and planning procedures related to hybrid resources with, as you saw from some of the earlier charts, substantial amount of these resources entering into the ISO interconnection queues across the US. So you see these 4 participation models on your screen now. I'm just going to talk very briefly about these. I should note that the models are fairly high level. There's much more detail that may be necessary for facilitation of participation of these resources, which is obviously part of those stakeholder discussions. I'll also mention that neither EPRI or Lawrence Berkeley, we do not advocate for using any one of the 4 models. We actually encourage a greater number of options that the assets or system operators can choose which works best for them given their situation, subject to things like reliability, fairness, budgetary requirements, and so forth. So that said, let's describe these 4 participation models. I'm actually going to move clockwise from the upper left and really just talk, as I mentioned briefly, about these. So on the top left, you have the separate independent resources. This is really if each of these individual resources would be interfacing with the ISO in terms of both operations and markets and how it is selected with and scheduled as part of the market, each as an individual resource. So for example, the solar resource can participate as a solar resource given forecasts and all of the different rules that are associated to variable energy resources or dispatchable intermittent resources and those other types of participation models. And then the battery would also participate separately, similar to the participation models that are a part of the ISOs are now finalizing from the FERC Order 841. So not a lot different there, minimal changes to existing market designs. Each of those individual resources can just bid like they would as an individual resource. There may be some limit on the inverter in terms of the sum that can be injected onto the grid, but otherwise these resources can just participate separately as independent resources. On the upper right there is the other side of that, and essentially what that means is that the hybrid resource is now interfacing with the ISO and participating in the market as a single resource. So the ISO doesn't have the information on any of the predictions or telemetry potentially of each of the individual resources, just as the resource as a whole. So this would be, essentially that resource would be, the aggregate resource would be putting in offers, maximum capacity, ramp rate constraints, and other parameters that reflect the aggregate of the hybrid resource, and then put in these bids to essentially reflect any of the constraints in terms of how it can be operated. But the ISO doesn't have the information of the individual resources. Moving down clockwise to the bottom right is what we're calling single resource ISO managed feasibility. We have a similar term that we've been using for standalone storage that we call state of charge management light. And essentially what that is that the ISO is receiving information, for example, in the hybrid's case, of the individual resources. However, the hybrid resource is still participating in the market as a single aggregate hybrid resource with offers and parameters reflecting the full aggregate resource. So the ISO in this case would not intervene, would not do anything unless it appears that based on the information, which might include, you can see that by the dashed blue lines on the bottom right. So it might be the forecasts of the renewable plant. It might be telemetry of state of charge for the battery, but individual information that it still is receiving. And if it finds that it's given a schedule that is infeasible, it could then limit that schedule to essentially for insurance of reliability. So in other words, if it would otherwise give a schedule that's not feasible, it would limit that schedule. And then now going to the bottom left, the final participation model, which we are calling separate resources linked. And this one's kind of, I should have mentioned at the beginning that there's lots of other configurations or branches of each of these four. This one potentially could be the most complex, but essentially what we're saying there is that these resources, each of the individual technologies that makes up the hybrid resource, can interface with the ISO, put in parameters, data, and offer curves with the individual resource. But if there is some mechanism or some feature that makes the hybrid resource unique and would make it otherwise operate differently than the individual resources, that linking constraint can be included. This is very similar to how a lot of the ISOs model combined cycle resources. So, for example, California and SPP and ERCOT each have what we call a configuration-based combined cycle model. And in that, each of the individual units might have individual offers and parameters, but there's also this linking constraint that says, look, if this configuration is on, then some of this parameters may be different. So essentially, it's having them each operate individually, but having additional information that shows the linking constraint. One of the most common what we think of as a linking constraint can essentially be the investment tax credit limit on grid charging. So essentially, that can be the linking constraint that can be added. Next slide, Will. So as I mentioned, the participation models that I described are fairly simple so far. We've got some ongoing research and other plans to dig deeper into this, to run simulations, to evaluate what potential other implications in terms of reliability and economic efficiency there could be. The details and the challenges that must be addressed differ depending on the different options, obviously, and certainly a lot of these challenges that you're seeing here exist with standalone storage as well as standalone renewables, and not necessarily negative challenges either, just different challenges that might need to be addressed, and they do not necessarily become more or less challenging with hybrid resources, but maybe need to be considered in a slightly different manner. So I won't go through each of these in detail. They're described within the report, but just sort of capturing a few of the key ones. So looking at forecasting, how does forecasting differ if they have the hybrid resource and the different participation models? Looking at market mitigation and physical withholding, how do you know what a verifiable cost is of the different participation model options? We have challenges such as computational tractability. So if you have a lot of these resources and there's very complex ways of representing them, we saw this with combined cycles, may it lead to additional challenges with how you are able to solve and clear the market within the timelines. Other things like valuing capacity credit, how much does the hybrid resource contribute towards peak needs, offer parameters, I talked a little bit about that with the participation models. Interconnection is a big challenge, obviously, lots of, some of that addressed with Order 845, but still lots of challenges that folks are bringing up, how you represent them in study models, as well as generally around metering telemetry. So a lot of these challenges, we talk about them within the report. I think there's a lot of follow-up work, both from the research organizations as well as the ISOs and their stakeholders that are now, initiating a lot of these initiatives around how to integrate hybrid resources today. So we'll see a lot of these being addressed as we go. With that, I'll hand it back over to you, Will.
Great. Thanks, Eric. That was great. So the next slide is just a conclusion slide. So I'll do this really quickly, and then we'll try to spend 15 minutes to get through as many of the questions that you all have. And I already see a great list. And if you have more questions, this is the time to add them. So overall, so what we talked about, to conclude, we found and show that commercial interest in generator battery hybrid plants is growing rapidly. So we saw that with the development data. With our price and market analysis, we showed that co-locating batteries with renewables offers significant potential value in some regions. Now, this was assuming historical prices for both energy and capacity services and no ancillary services. So in California, we found that energy and capacity value boost exceeds costs, but there is some future work that we mentioned that would be needed, and in particular, understanding how to predict hybrid capabilities to maximize their value under evolving market designs. And so this is basically, in other words, understanding how these would get dispatched into these markets and some of the bidding strategies that these technologies would have to truly pin down their value. And then we also showed that independently sited batteries could capture even more value, but they will, of course, lose the cost synergies. And so I think one additional area for future work is to better understand the total cost savings from hybrids versus standalone projects. We mentioned this qualitatively a little bit earlier, that there's these synergies, but there is very little kind of real-world data that exists to understand how big those synergies are, and most of the current analysis has been from bottom-up kind of engineering designs. And finally, Eric presented on participation models and showed that these need to be developed considering the challenges and opportunities for the hybrid technologies. And it's kind of an open question on how to model and enable these hybrid systems to most benefit market operators and to help general kind of regulators and industry decision makers make long-term planning decisions. And so there just is, in general, more work that is needed to understand, you know, the full range of opportunities and constraints. So with that, I thank you for listening and hanging in there for the whole presentation. And so we will now try to, in some organized fashion, work our way through the question and answers. Andrew, I don't know if, so I've spent some time looking through this, but do you have
I do have
organized
a list.
sense?
Yes, I do have kind of some organizations here. I think what we'll do is just sort of start through this kind of in the order of the presentation a bit. So I'll go through them, and then there are lots of questions, so I just encourage you to keep the answers brief when possible. So first question was just whether or not we've considered, or is there sort of a benefit to transmission lines in terms of spreading out costs or congestion reduction for hybrid plants?
Yeah, so this is it's a great question. We didn't do any type of formal analysis of transmission constraints necessarily, but we did find is that you know, these hybrid projects, the queues are packed with projects, and so the transmission system is definitely having to deal with that issue and triaging between which projects go online. And so one of the reasons that these hybrid projects have become popular is because of that overhead that might exist from interconnecting and paying those transmission costs. It be cut or reduced by having, you know, the co-location happening, because you don't have to go forward with two applications, you just go forward with one. But in terms of a more detailed transmission analysis, we did not do that for this work.
Okay, and then early on in the presentation, you mentioned that storage in some cases can only charge from co-located solar. Could you just explain why that would be?
Yeah, so that was mainly due to the ITC constraints. So we were thinking, so to qualify for this investment tax credit, this 30% tax credit, you have to charge the battery at least 75% from solar or wind. And so for this analysis, we implemented the most stringent constraint just to see how big that reduction in value would be from adding that constraint. But in reality, once the ITC goes away, or the fact that you only have to do it for 75% of the energy, that constraint would be relaxed. And so in future work, we're going to try to understand the impact of relaxing that constraint. But here, we just wanted to see the largest grid charging constraint, and it was driven by this ITC rule.
Okay, and did we ever find that it was economical to capture the clipped energy when you had a DC coupled system?
So we haven't done that analysis yet. We didn't do it here. We didn't present it here. It was all AC coupled systems. Again, this is an area of future work where we've created a DC coupled system in our optimization model, and we're going to start to explore that value of clipped energy in the future. So definitely keep an eye out for future reports and webinars that will present on that topic.
Okay, and somewhat related to that was just a question asking if the hybrids in practice are ever configured in a way where they can sell energy directly to the grid without going through the battery.
So I think that is absolutely the case. If you are even DC coupled or AC coupled, you could have a system in place where the battery, the flow from either the PV plant or the wind plant or whatever generator, the flow just goes through the generator's AC inverter and interacts with the grid and sells directly, and the battery doesn't do anything. So that definitely can happen. And there's definitely times, even in the models, when you were looking at the time series of the optimization models that we came up with, the battery doesn't do anything. It's kind of just sitting there in the background, either holding charge or being empty. And it's just the generator that's interacting with the grid. So the battery does not always have to be operated to generate and interact with the grid.
Great. Okay. Now moving on to some of the questions about the deployment data. Just one quick one was, what was the source for the deployed projects? How did you come up with this list of projects that were actually deployed that were hybrids?
Yeah, so the online list that we have was developed using a combination of EIA 860 data and finding when the EIA ID, so the ID that kind of locates the power plant, when that ID matched with another battery. So sometimes there's the wind plant will have that ID, and then the battery will have that same ID. And so when that existed, we denoted that as a hybrid project. And then we did some pretty detailed review. Mark Bollinger led this work of press releases to confirm that those projects were in fact hybrids. And so that's the main source of that online data is the EIA. And so one issue with that is that there are some customer-sided, so behind-the-meter projects that are in that data set, which isn't necessarily on the wholesale market operation side of things. And so that is a little bit muddied in the data that we had to use because we couldn't really distinguish between customer-sided and not, but they are all larger than 1 megawatt. So these are pretty big systems.
Great. And then one question was whether or not the ISO queues, which you reviewed, do they provide enough information to determine the relative size of storage versus the generator capacity? And do they also provide enough information to get out the duration of storage?
So the second question, we did not have any information on the duration of storage from those queues. And then the first question, it depends. So some of them do provide that information. So CAISO's queue does. And I can see real quickly, see if I have this extra slide in here. And so on the ones that do provide this information, such as CAISO, you can see this solar to battery capacity ratio. But that is not true about all of the queues that we reviewed. And yes, we did not present that data here. But what we found here is that there is a correlation between the markets and which one have the highest battery to PV ratios. And so CAISO, California in particular, had the largest ones, which kind of comports with this notion of the duck curve and California being where there's the most value for battery projects, at least using current prices type of analysis.
Okay, thanks. And now kind of moving on, just in the interest of time, to the questions on some of the costs. How was it that you calculated the dollar per megawatt hour PPA price adder when adding the storage to hybrids? Did you account for losses, or are these megawatt hours delivered?
Yes, these are megawatt hours delivered. And the explicit details, I'm not the best person to answer them, as Mark did most of this work, but my understanding is in a number of the PPA contracts that Mark reviewed, there were explicit details on the capacity value that these projects were acquiring when they were contracting with the PPAs, and it broke it out by energy and capacity value, and using that, you could explicitly extract this storage adder on megawatt hours delivered. But all of the assumptions that kind of went into what that megawatt hour denominator is, for instance, like the capacity factor on that storage, I'm less clear about, and Mark would know best.
Okay. You noted that the Hawaiian costs were somewhat higher. Is this because they offer higher functionality, such as providing fast frequency services, or is there some other underlying reason for the higher costs?
Yeah, I think, from my opinion, the biggest driver is probably the fact that the competing technology is oil in Hawaii, and so the electricity prices are just higher, and so PPA prices are higher. But I do not know the details of these PPAs. I have not reviewed them myself to see whether or not there are additional services that are being provided. But it could be an island system is much harder to balance than a larger grid system, and so it could be the case that these batteries are going to cycle more or be used for more services because of the additional needs of an island system. So that definitely could be a part of the story here, either via degradation costs being higher, so these PPAs need to be higher, but again, would be a question for Mark, who was the real researcher who looked into the details of these PPAs. Okay.
I'm going to now shift gears towards some of the questions on the value analysis. One of them was, do the batteries influence prices at all in our perfect forecast scenario?
No, so this is a price taker analysis, and we just took prices as given and didn't have a full kind of model that projected how prices would change.
Okay. And then in the imperfect foresight case, did we do anything to address issues of going from sort of an on-peak Friday to an off-peak Saturday? Was there sort of any recognition of weekends in that analysis?
So I guess to understand that, I don't know if I fully understand the question, but this was an hourly kind of time series analysis. And so when we did this day before, we never did any kind of adjustments for weekdays or weekends. It was, so if you were dispatching on a Saturday, we looked at prices on Friday and then implemented that on Saturday. And now I think what that suggests is, yeah, well, those Friday prices are probably going to be very different than what happened on Saturday. And so that would be a suboptimal dispatch. And that's definitely not ideal, but that's somewhat of the idea of that algorithm, is we wanted to get the worst case that is implementable in our mind. And so it is, maybe there's no doubt that we could improve that. There are sophisticated techniques to improve that, but we did not implement those here. And so that's why our range is pretty large. And so the goal is to find different algorithms to tighten it.
Great. And then we're in that analysis, were all of the prices based on real-time prices? And if so, what would you expect between the difference with day ahead versus real-time prices?
Yeah, so these were all real-time prices that we used here. And in terms of the day ahead versus real-time, I think real-time prices are more volatile than day ahead ones. And so there's arguably a larger ability for storage to take advantage of that. And so that's definitely happening in the perfect foresight case. It's taking advantage of that volatility. In the low value case, it's not really taking advantage of that volatility because you're using yesterday's prices. And so it doesn't show up there as much, this difference. But that is something that we're looking into for future work, to think about if we can use day ahead prices to schedule in the real time, and we might explore this in more detail.
Okay, and with the last few minutes here, I'm just going to turn to a couple questions on the participation models. And so these are for Eric. Just at a high level, could you just say a little bit about how hybrids would actually capture some of these values in existing markets in terms of energy, ancillary services, and capacity markets?
So I think, so the question is, how would they capture value using existing participation models, maybe?
Yep, just if you could give a flavor for existing practices.
Yeah, so, as I mentioned, the FERC 841 did say that, any sort of hybrid resource, while it was out of scope, they could use the storage participation model. And as also a lot of the model I mentioned, the separate, independent, that's something that can be done today as well. So there is a lot of that option, and so there might not be the full flexibility of how to participate, but a lot of that is still there, and they can. Now, some of the rules around which ancillary services, for example, they can participate in, still a little bit murky, but yeah.
Great. And then another one was, are there any best practices that you've seen so far for estimating the capacity value of hybrid projects? And do you have any sense of sort of how that's being settled in some of these markets?
Yeah, so far within the markets, as far as I know, and not obviously being able to follow this on a regular basis, but I believe in California ISO, their procedure so far is to take the how they do capacity value for renewables, which is based on effective load carrying capability, and how they do capacity value for storage or batteries, which is effectively the amount of energy they can discharge within 4 hours. They just add those two together, and of course, if there's any limitations on inverter or other limitations on how much can be injected, that takes into account as well. We do have some research, and I think both Lawrence Berkeley and EPRI have done some research on how to do this and how to use more advanced models to actually capture ELCC, effective load carrying capability, to look at how this differs of a hybrid versus standalone storage and a standalone renewable. And I think that a lot of those studies should help out as the ISOs and other utilities are looking into what that contribution is to help them with peak planning designs.
Okay, great. Thanks, Eric. And we are at the top of the hour. There are a number of questions that we didn't get to during this presentation, but what we'll do is collect those questions and we will follow up via email to those people whose questions we weren't able to get to. And we just wanted to thank you all for participating with this webinar today. We hope you're all staying safe and healthy at home, and look forward to having another presentation with you all sometime soon. Thank you.